Good morning. I'm Jacob. I'm joined by Seth, Jack, Muskan, and Ann, and today we present to you BioDilute, our process to produce biodiesel and crude glycerol using a reactive distillation column. To start our presentation today, we will introduce you to the idea of BioDilute, then you'll be given a process overview. Following that process overview, we will talk about the safety aspects of our plant, then the environmental impacts, and finally finish up with our economic analyses. So what actually is biodiesel? Biodiesel is a plant project to produce pure biodiesel from waste cooking oil that would normally be sent to landfills. Pure biodiesel, also known as B100, when combined with traditional diesel fuel creates a cleaner burning fuel, as well as other benefits. These other benefits include a much lower net carbon dioxide emission, as much as 78% less as estimated by the EPA. BioDilute also provides additional economic stimulation with little resource consumption through the means of value-added refining of a waste product that would typically be sent to a landfill. The fuel created is not only more sustainable, but imposes no disruption on the food chain like other processes which use corn and soybean oil to create biodiesel. It also provides monetary incentives for restaurants to get rid of their used cooking oil instead of reusing it several times, which has been linked to causing cancer. Finally, it has benefits for the engines that use it, providing better lubrication and extending their longevity. Keeping these benefits in mind, BioDilute has the following goals: to create a profitable, safe, environmentally friendly biodiesel production process. The project has the following production goals: 2.5 million gallons of B100 per year and 400,000 gallons of crude glycerol per year.
For our process, we start with esterification of the free fatty acids in the waste cooking oil with sulfuric acid and methanol, followed by trans-esterification with sodium hydroxide and more fresh methanol. And then after trans-esterification, we separate out the FAME and glycerol to sell high purity product to match regulations and recycle methanol back to the trans-esterification. Normally, waste cooking oil is thrown out as waste by restaurants and is a loss for these businesses. With us, we will have a third party collect and filter the solids out of the waste cooking oil and use it as the feedstock for our process to generate biodiesel. Solids need to be filtered out, otherwise the process can't proceed without problems, especially the pumps. For our waste cooking oil compositions, they'll be of triglycerides and their respective acids, such as trilinolein and linoleic acid, triolein and oleic acid, and tripalmitin and palmitic acid. The free fatty acids present in the waste cooking oil initially need to be converted, otherwise in our trans-esterification reaction, these acids will react with the base catalyst and form soap, which will reduce our FAME conversion and create problems with separating the glycerol and FAME. To prevent this, the free fatty acids on a weight basis must be less than 1.5% of the total mass entering the trans-esterification column, which is the purpose of the esterification reactor.
Like stated before, the first step in our process to produce biodiesel is esterification, which is an established technology that bears less risk. This is to reduce the FFA below 1.5% to prevent saponification by reacting with an alcohol and a catalyst to convert it to fatty acid, methyl esters, and water. The alcohol for our process is methanol due to it being economical, has a higher reactivity with FFA, and available in large quantities. Our catalyst was sulfuric acid, which was used to protonate carbonyl groups of the FFA. There were a total of 6 reactions in the CSTR, and the product has some separations and sent to the next phase. The next step after reducing the FFA below 1.5 weight percent is for the trans-esterification process by reacting the waste cooking oil with methanol and a catalyst to convert it from triglycerides to methyl esters with diglycerides and monoglycerides as the intermediates. This will also be at a ratio of 6:1 methanol to waste cooking oil. In total, 34 different reactions occurred during this process in order to produce fatty acid methyl esters, or FAME, as well as a byproduct of glycerol. There are many different catalysts which will be discussed later. However, for BioDilute's process, sodium hydroxide or homogeneous base catalyst is used to result in fast reaction rate and high conversion. Also, it is very economical. There have been lots of studies on different types of ways to conduct trans-esterification, especially through the various reactors. For our experiment, we will be focused on catalyst-based reactors instead of ways like supercritical reactions to avoid high energy costs. These consist of batch, membrane, and reactive distillation. Batch may have a high conversion, but is not practical in a production environment for its cumbersome mode of operations. Membrane is the most recent discovery for this type of reaction, and has a lot of pros consisting of environmental. It doesn't require a lot of treatment to do so. However, it's very newly researched and does not have a lot of data on production scale. The reactor we ended up choosing was a reactive distillation column because it uses little energy and reduces the carbon footprint. It may have other cons like corrosive catalysts or having to have a neutralization stage for the catalyst, but was the most practical and economical choice. Like stated before, there are many different catalysts that can be used for the transesterification process. Our process was a homogeneous base catalyst or sodium hydroxide for its economical feasibility, and it is beneficial since it is less energy efficient and high conversion. However, the FFA percentage needs to be low in order to prevent saponification. This was chosen over the other processes like heterogeneous base because it also has this saponification problem, but also catalyst leaching. Homogeneous acid was much slower and had difficulty separations, and finally heterogeneous acid was extremely high cost and energy and also had a long reaction time. Therefore, a homogeneous base catalyst and sodium hydroxide was our choice of catalyst. After the triglycerides have been effectively converted to FAME and glycerol, the products now need to be separated and purified of any contaminants. The glycerol and catalysts specifically need to be separated to increase the purity of our products. This is done through water washing and an extractor to remove the catalyst, methanol, and glycerol in a separate stream from the FAME. Then this FAME is refined in a distillation column to produce the final product. The separation of the glycerol, however, is put through a CSTR to neutralize this catalyst to be able to safely discard, which is done through a decanter. Then after the water and salts are removed from this decanter, the glycerol is purified through a distillation column to produce the final product and get ready for it to be sold. Here is a process flow diagram or PFD to showcase our process. First, the waste cooking oil goes into a CSTR for the esterification. This is along with the alcohol, methanol, and the catalyst sulfuric acid. There's also a recycle stream later down on from a distillation column. After this, the FFA is reduced and then sent to an extractor where the glycerol is input in an extractor with it to remove that catalyst and put it through a distillation column where the catalyst is put into a waste stream and the top of this distillation column is recycled back into the CSTR. The extractor product is then put through a reactive distillation column for the transesterification, where it's put in with the sodium hydroxide catalyst, methanol, and other recycle streams from further down in the process. This converts the triglycerides to the FAME, and this FAME with the NaOH and the glycerol is put through an extractor. And this is water washed, where the FAME is put out into the distillation column and separated from the other products to create the final product of FAME. And then the glycerol separation is put through a CSTR with phosphoric acid to be neutralized, and then decanter removes this solid waste. And after the solid waste is removed, the distillation of this final glycerol product is created, and then the final glycerol is produced.
For our technical assumptions, we have our CSTR and reactive distillation column operating isothermally. Our distillation columns operate with negligible pressure drop. Our waste cooking oil obtained is above 2% free fatty acids, requiring the esterification process. No reversible reactions are modeled because the methanol is fed in an excess of 6:1 molar ratio to ensure the forward reaction occurs, and the waste cooking oil is brought pre-filtered with all the solids removed. Here's our overall P&ID diagram. The esterification is the first part of the process, followed by the transesterification process, and ending with the FAME and glycerol purification. Here's a close look of the esterification process. The pumps used in this area are positive displacement due to the high viscosity of the waste cooking oil, and the materials of construction for every unit is 316 stainless steel to protect against the corrosion from the acids. For esterification, our CSTR operates at 60 degrees Celsius and 4 bar, a residence time of 2 hours to ensure the free fatty acids have enough time to react. There are 6 total reactions modeled, 1 free fatty acid for each triglyceride present. Our conversion is 97% of the free fatty acids to FAME, ensuring we are under the limit of free fatty acids for the transesterification reaction, and that a saponification reaction will not occur between the remaining free fatty acids and the base catalyst during the reaction. Our extractor uses glycerol to separate the waste cooking oil and FAME from the sulfuric acid, water, and some of the methanol. The sulfuric acid stream flows into a distillation column, where the sulfuric acid, water, and methanol are the bottoms outlet, with the majority of the methanol being recycled. More methanol could be recycled by increasing our boiler duty, but it provides diminishing returns, and the utility cost becomes increasingly expensive for only a little more methanol being recycled.
After the esterification process of removing the FFA to prevent saponification, that product is then pumped from that into the transesterification reactor with the NaOH, the catalyst, a new methanol feed, a recycled stream of methanol from the distillate of this reactor, recycle from the FAME separation, and a recycle from the glycerol separation. It is then put through that at different stages, and then at the bottom of it is where the triglycerides react to form FAME. And it's put out and went through the rest of the process to be purified and separated. After lots of optimization and sensitivity analysis in Aspen, these factors for the transesterification reactor were concluded. 30 stages, 60.85 reflux ratio, reboiler duty, and waste cooking oil flows in at stage 3 and recycled methanol at stage 12, with the reactions taking place between 3 and 29 with a 2-hour residence time. This results in a distillate of 55 kilograms per hour of leftover methanol that is recycled, and that triglycerides are converted into FAME with a 98.7% conversion, with a byproduct of the glycerol as well. After the transesterification portion of our process, it is then set to an extractor to be water washed with the glycerol, sodium hydroxide, water is sent to the bottom of the extractor where it's purified. And then to the right of it, the FAME is then sent to a distillation column where it's purified of a leftover methanol. And then after that, the methanol is then recycled back into the beginning of the transesterification portion, and the final FAME product is produced at the bottom. After optimization analysis and sensitivity analysis for the extractor and distillation column, here are the factors that were concluded from that. The extractor was set to be at 4 stages. Products water washed to separate glycerol, and the FAME leaving contains less than 1% vegetable oil, methanol, water, and the catalyst. And the distillation column that was used to purify this FAME was at 7 stages, 1.4 reflux ratio. Most of the methanol was recycled from the distillate back to the transesterification, and 99% purity of FAME was reached. And in total, 350 gallons per hour of FAME is produced through this process. To continue from the extractor, the glycerol, sodium hydroxide, methanol, and water that was separated from the FAME was sent into a neutralizer, which H3PO4, and after it was neutralized and it was safe to dispose of the catalyst, it was then put through a decanter where the water and salts were extracted, and the crude glycerol was sent to a distillation column to be purified, where the distillate was recycled with glycerol and methanol back to the transesterification portion of the process, and the glycerol was refined to be sent to the bottom. Here is the process after optimization. The neutralizer was modeled as a CSTR. The phosphoric acid reacts with sodium hydroxide to neutralize the base as a salt for safe disposal. Salt and water will be separated as waste through a decanter, which leaves glycerol with the residual methanol, and then finally, for the glycerol purification, through this distillation column, it was set at 7 stages. 1.4 reflux ratio at a total condenser operates at 0.4 bar to prevent from reaching degradation temperature, and the glycerol reaches 92% purity with a production rate of 55 gallons per hour. In conclusion, our B100 biodiesel was produced at 2.9 million gallons per year with a purity of 99%, which is well above the regulation 96.5%. And the glycerol was produced at 450,000 gallons per year with 92% purity, which is well above the crude glycerol purity levels of 80%. In conclusion, not only did we reach the purity levels that needed to be sold, but we also reached well above our initial projected goals of our production per year.
So now we'll be moving into a safety analysis of our plant and our process. The table in this slide shows some of the chemicals, their hazards, the flammability and explosion, and the protection measures, as well as the stability of the chemicals. So these were the chemicals that were chosen because these are the ones that operators can potentially be exposed to because they are either direct inlet or outlet streams. But it is also good to note that some of the saturated fatty acid chains that are produced as intermediates can be irritants, but since they are not ones that are directly exposed, they're not as concerning as the ones that staff can come into direct contact with. To combat the corrosive nature of most of our chemicals, stainless steel equipment will be used, and to combat the irritation that most of our chemicals do also, adequate ventilation and personal protective equipment are required at all times. Moving on, we can see the NFPA symbols and the GHS symbols for some of our chemicals. Methanol is classified as a 3 for flammable, with the largest value in these sections being 4. So this shows that methanol is actually highly flammable. It is also a 1 for health. Sulfuric acid and phosphoric acid are classified as a 3 for health. These are very strong irritants and toxic to human consumption and ingestion. Phosphoric acid is classified as a 2 for instability. It is highly reactive when it comes into contact with other chemicals. And sodium hydroxide is classified as a 3 for health and a 1 for instability. It is only unstable under excess heat. The GHS symbols can be seen in the red outlines of the diamond shapes. The top left-hand side shows corrosion to skin, which is applicable for sulfuric acid, phosphoric acid, and sodium hydroxide. The top middle one shows flammable, which is applicable for methanol. And the top right-hand side shows environmentally damaging, which is relevant because we are using sodium hydroxide. Moving on to the bottom row, the bottom left-hand side shows an irritant and acute toxicity, which is once again related to phosphoric acid. And then the bottom left right-hand side shows a health hazard, which is identified with methanol. Now moving more into process safety, this process safety plan will ensure that staff and community members are kept safe during operation. Firstly, potential hazards will be identified. So for example, liquid methanol leaks from storage tanks or accidental vapor release from methanol recycle streams will be identified as some potential hazards. The risk of each hazard will be assessed. So for example, human toxicity when methanol is being ingested, or potential ignition if methanol vapor is met to an open flame. Some of the safety measures that we'll put in place is level sensors on methanol storage tanks to detect leaks, as well as some pressure relief valves, as well as other valves on our recycle streams. Employees will be trained on handling harmful chemicals and to not have open flames on the production site. Safety inspections will be done and regular preventative maintenance will also be done. These regular inspections will ensure the equipment is up to standards, and for example, preventative maintenance can help corroding valves when methanol is being passed through it. Lastly, incidents are inevitable. Proper response and communication of these incidents make the impact lower. Here at BioDelu, we advocate for effective communication to the nearby communities. This will be done through transparency, as this builds trust, and this ensures that the community members will act on any accidental releases. So in order to have an effective plan, we need to identify key community stakeholders. Children and pregnant women will always be top priority for our community stakeholders. Secondly, we need to understand the community concerns. By conducting surveys and making the potential risks, such as methanol vapor release, will allow BioDelu to know what risks are important and what risks are essential to report to the public. Thirdly, an effective communication media is essential. Reporting in newspapers would probably result in low coverage. Utilizing news channels that can be displayed through the television will be more effective. Also, a timeline of remediation and risk management will be shared with the public. This will allow community members to know when they're able to move back into their home if they ever have to evacuate. Monitoring and evaluating the ongoing incidents will also allow for better communication. And then lastly, building community engagement through community events will build trust, which is essential for safety. If community members do not trust the professionals at BioDelu, they will tend to not follow the emergency responses that we would put in place, and this can be very unsafe for health.
While community communication is important, an accident must be avoided at all costs. To do this, a full hazard assessment of the plant has been performed. Here, we have the HAZOP of a key section of our process, the transesterification reactive distillation column. For this process, we are considering deviations of high or low for 4 parameters: flow, level, temperature, and pressure. In our initial design, there weren't no safeguards other than those inherent to the process. In accordance with the identified hazards, a control scheme for the transesterification portion was designed and implemented. Moving on to our P&ID, including control considerations, several parameters have been addressed. For pumps and heaters, temperature control and emergency shutoff have been added, as well as bypasses to avoid pump overheating. For the reactive distillation column, temperature and pressure controls have been included, with a special emphasis on temperature. The exothermic nature of the reaction demands greater control, so control schemes have been added to both the condenser and reboiler. Pressure relief, both feedback and emergency, have been included, with the emergency leading to a flare to reduce flammable vapors escaping in the plant. Finally, manual control valves on the recycle are included to allow their isolation during startup or maintenance.
For our transesterification process, we have a fault tree in regards to the temperature decomposition of our flame. We have 2 initial events that could be happening, either insufficient cooling or excess heat. For cooling, there could be a temperature indicator failure, or the cooling could have completely failed, which for the cooling to have failed, there would either have to be the valve for the cooling water in the condenser to have failed, or the condenser is leaking and unable to properly cool the methanol in the distillate. For excess heat, there could be the wrong addition of reactants, which could either be the catalyst is undercharged or the reactants are overcharged, and the column isn't able to operate normally. The reboiler could also have failed, which likely could be the result of a temperature switch failure, or the temperature indicator failed, leaving operations unaware of the problem. Or the reactants could be accumulating in the column, most likely would be methanol, and this could be the result of the outlet valves being in the closed position without knowing, or they have failed. With the amount of methanol present in the reactive distillation column, an overpressure scenario resulting from an explosion was calculated with the equivalent TNT method. The steady state operation will be at 230 kilograms an hour of methanol, and with a residence time of 2 hours, this comes out to 460 kilograms an hour, assuming the esterification inlet pump shut down suddenly. The control strategy failed to identify operations of this. In case of any accumulation, 500 kilograms an hour was also measured. 200 and 300 meters are the distance from the explosion, and the resulting overpressures felt at those ranges. At 200 meters, an explosion will create an overpressure to cause minor damage to houses in the area, and 300 meters resulted in a safe distance overpressure, such that the probability of serious damage is less than 5%. To minimize damage to housing, the fence line from the transesterification column should be at least 300 meters away on a worst case basis.
So now we're going to move into the environmental impact that our project has. We will be comparing the environmental impact when we have a methanol recycle streams or no methanol recycle streams. So this environmental impact analysis will be done by using the waste reduction algorithm by the EPA. This shows the potential environmental impacts per hour. I-out stands for output, and then I-gen stands for generation. For global warming, we can see that with a methanol recycle stream, there are about 100 potential environmental impacts per hour. However, without a methanol recycle stream, this skyrockets to about 700 potential environmental impacts per hour. This is because the methanol vapor stream from both the transesterification and the esterification distillation towers would have been released in the form of vapor. So this significantly increases the potential environmental impacts with respect to global warming. Also, it is good to note that for both processes, there is no generation of any potential environmental impact that could affect global warming or contribute to it. Lastly, under environmental impact, we will need to consider disposing of the waste. Waste from esterification does contain about 70% methanol and 16% sulfuric acid. It does need to be collected in a sealed stainless steel container because methanol is flammable and sulfuric acid is corrosive to metals. According to the EPA, any form of waste containing methanol does need to be released and disposed of through approved environmental health and safety personnel. So we will contract a licensed waste solvent company that is approved by local EH&S branches to dispose of this waste. And then our solid waste from the neutralizer contains about 12% trisodium phosphate. Trisodium phosphate is not harmful in any way, so this can be disposed through the septic system.
Now we're going to talk about the economic analysis of the project. Here's the market analysis of B100 biodiesel selling price per gallon from 2005 to 2022. As you can see, biodiesel price has been steady around $3.50 with slight deviation throughout the years. However, up until last year, it surged up to almost around $5.5 and has been like this for a year now. And this shows that this is a profitable time to start manufacturing and selling B100 biodiesel. Here's our main economic assumptions. Additionally, we also assume that the plant is operated for 8,400 hours a year. Cost for repairing and maintenance is 5% of our fixed capital investment. Salvage value is negligible. Startup expenses is 10% of FCI. Plant overhead is 65% of labor, supervision, and labor overhead cost. In this table, we present our cost of material per gallon, and in total, we spend around $4.2 million on raw materials a year. Here's the list of our equipment. We obtained the cost from Aspen and Alibaba. The Chemical Engineering Plant Cost Index used was 808.7 for December 2022 to estimate the total equipment cost. Our cost of equipment for this plant is $1.3 million. Equipment in biodiesel industry is mostly made of stainless steel and carbon steel, since these have proven to be resistant to corrosion and degradation. Material of construction for each equipment is also provided in the table. To estimate the fixed capital investment, we included direct costs such as equipment costs, installation, instrumentation, piping, and electrical, and indirect costs such as engineering, supervision, construction expenses, contractor's fee. Here's the breakdown list of our direct costs and indirect costs, and our fixed capital investment is around $4.7 million. Based on a calculation from the previous slide, our FCI was $4.7 million. We estimate the working capital by including raw material and value of product and byproduct inventory, cash on hand, accounts receivable, credit for account payable, and that sum up to around $2 million for working capital. The startup cost is assumed to be 10% of our FCI. Land cost in Pasco County is estimated to be $400,000. Therefore, our TCI is around $7.2 million. In this slide, we consider the economic feasibility of the project. Net present value is the process value considering the time value of money at year 0, which is $2.6 million. Equivalent annual worth is around $860,000. Discounted cash flow rate of return is estimated when NPW is 0, which is 22%. Rate of return is the ratio of average net profit for the first 6 years to TCI, which is 19%. Benefit to cost ratio is the ratio of the sum of cash flow in operating years to the sum of cash flow in investment years, which is 2.9, and payback time is calculated by taking the ratio of TCI to the average of cash flow from the operating years, which is 3.27. Figure 13 shows the non-discounted cumulative cash flow with the minimum rate of return of 15%. Year -2 includes the cost of land. Year -1 has 50% of FCI. Year 0 has the rest of FCI costs and working capital and startup cost. Starting from year 1, we start to take into consideration the depreciation using micro method. Depreciation period ends in year 8, and in year 10 we recover the working capital. Figure 14 includes 3 different economic scenarios where we change our biodiesel selling price, waste cooking oil buying price, glycerol buying and selling price, operating labor cost, and FCI. For the optimistic case, we increase our biodiesel and glycerol selling price while decreasing waste cooking oil and glycerol buying price, as well as operating labor cost and FCI. The most likely scenario is obtained from our data, and the pessimistic curve is the opposite of the optimistic scenario. Figure 15 provides an overview of the discounted cumulative cash flow with different minimum attractive rate of return. As shown in the graph, the lower the minimum attractive rate of return, the higher the discounted cumulative cash flow, which means the project makes more profit. For the sensitivity analysis, we considered some important variables such as biodiesel and glycerol selling price, waste cooking oil and glycerol buying price, operating labor costs, and FCI. We chose these variables because they contribute a significant amount of money to our cost. Biodiesel selling price depends on the diesel price, waste cooking oil and glycerol price depends on the source. Operating labor costs and fixed capital investment contribute the most to the operating cost of a plant. We provide the base value in the table above, and from figure 16, net present worth is the most sensitive to the change in cost of biodiesel and waste cooking oil. Any change less than 6% from the base value of biodiesel price result in a negative NPW, and any change above 8% of waste cooking oil price result in a negative NPW as well. Therefore, these are two of the most important factors to take into consideration when doing the economic analysis for the process.
To pair with the sensitivity analysis, we also created a risk analysis. Just like the sensitivity, we also use the same uncertain variables of biodiesel price, waste cooking oil price, glycerol, buying and selling price, operating labor cost, and FCI. We did extensive research on the lower and upper range of these values in the market, as well as the standard deviation of each of these to be more realistic. We then did 2,000 iterations and Monte Carlo simulation with these uncertain variables. As you can see, the frequency of occurrence can be seen versus the MPW in $1 million. The risk of loss of it going below 0 NPW was 23%, while the mean of our process was $2.7 million in MPW.
Biodiesel production in the Tampa area has a high probability of being profitable with reactive distillation for transesterification. Reactive distillation has proven to have a high conversion rate of FAME and glycerol from waste cooking oil, but the new neutralization step has a slight problem with creating aqueous waste. Overall environmental impact has been minimized with recycling methanol as opposed to venting it off. Safety is paramount for running the process and for the community, and even though we have applied safety in depth, it is essential for the plant to be built away from communities to minimize potential hazards to them in the case of emergencies. For recommendations, the esterification process could have used reactive distillation as well, and it would combine two of the unit operations in one, saving costs on utilities and equipment. There may have been even a higher conversion, so this could have been better than what we had done. As well as research on waste alcohol may yield better savings than using only fresh methanol in the feeds, but this would need a good bit of research on acquiring the waste alcohol and any impurities that could come along with it and how it reacts with the system and how to treat that. While we use sulfuric acid for our esterification catalyst, sulfonic acid, from some of our research, looks like it could be a better catalyst and increase the yields from our CSTR, and potentially you might need even less of it compared to sulfuric acid. As well as this, potassium hydroxide could have been used instead of sodium hydroxide, and the kinetics may be similar, but potassium phosphate would have been the result from the neutralizer, and this could be sold as fertilizer. But it would require additional steps to purify as a sellable product. And our final product streams of glycerol and FAME, those are at higher temperatures than the rest of the process, about 100 degrees each, and this heat could be recycled in the rest of the system through some heat exchanger networks. For startups, you would need to use some heating utility initially, but once you start to get at this point in the process, the heat exchangers could be used and you could start saving on utility costs. And finally, membrane reactors, these would reduce the amount of wastewater in the process, which our separators and neutralizer deal with. However, extensive research would be needed on modeling the reactor in Aspen or MATLAB, as well as specifications for the reactor, as we could find very little information on membrane reactors from our initial searches, aside from the potential benefits. And for acknowledgements, we would like to thank Dr. Sanal for providing us with continuous information on our process, Dr. Kuhn for being our faculty advisor, Dr. Schimmel for assisting with safety and HAZOP considerations, and Dr. Pettit for helping with presentation details and P&ID considerations. Thank you all for your help in making this project come together.